Hi, folks. Welcome to today's lecture on 6.4 Other Integration Methods. All right, so we're going to focus on a few more ways to integrate things that look a little bit more complicated today. And so in particular, we're going to do two specific skills. One, we're going to revisit the idea of approximating the value of a definite integral using something called the trapezoidal rule and Simpson's rule. And the second thing we're going to take a look at is how to use this table of integrals that comes in the back of every calculus book to solve integration problems. Okay, so my hope is that today is going to be a little bit of some revisiting old concepts and also helping us see that there's other tools other than the techniques that we've learned already so far. Okay. All right. So let's take a look at the concept here, because concept is always really important. All right. So when we see a graph, any graph doesn't have to look like this. But if someone were to say, I'd like you to find the area under this blue curve from x equals 1 all the way to x equals 4. And so they want you to find all of this area. We do that by finding the definite integral. Okay? So when you first learned about this integral, I hope that it was made clear to you that that when we find a definite integral, what we're really finding is the area under the curve that we have. Okay, so in particular, we have this curve, we have our x-axis, and all that space in there, that area is represented by the integral from 1 to 4 of f of x dx. Okay. I'm going to actually have us write it out in words just because we can't ever have too many places to keep things in our brain. All right. So under area under the curve. All right. And this is actually going to be important to know this is exact area. Okay. So let's say that we evaluated this integral and we got like 1.98754. That would mean that this area was 1.98574. Okay. All right. Now, you may wonder why I've now copied the same picture 3 times. Okay. And what we're going to do is just revisit, hopefully, a technique you learned back in 121, talking about approximating the area, okay? So we're going to start with this diagram over here, all right? And if I were to cut this space into sort of 3 rectangles, let me make these lines a little thicker, so 3 rectangles, okay? And if for each rectangle, I started from the left-hand side, so these 3 y values. And so I got like a height of 1 for the first rectangle, a height of 5 for the second rectangle, height of 7 for the third rectangle, okay? And not being particularly fancy, because we're coming from the left-hand side, we call this a left rectangular approximation method. Okay, so the L stands for that left y value. All right. And then we can only assume that if we can divide these into 3 rectangles and come up with heights that are from the left, well, we could also do that from the right-hand side, right? So for the first rectangle, I could choose the right y value. And for the second rectangle, I could choose the right y value. And for the third rectangle, I could choose that right y value. And that would give me something that looks kind of something like this. Okay. And these we called right rectangular approximation, or RRAM. And when we had LRAM and RRAM, it was important to note these were just approximations, right? We can see that, like for the LRAM, we're missing big chunks of this area. And for the RRAM, we're sort of overestimating these chunks of area, okay? And turns out that at some point, someone was like, well, maybe we could just split their difference. Instead of saying LRAM and RRAM, what if we had a middle rectangular approximation, like a midpoint, okay? And so let's take a look at what this might look like. We divide that space into 3, okay? But this time, and let me zoom in on this first rectangle, instead of choosing the left y value or the right y value, I actually choose the y value that is literally at 1.5, okay? So if we approximate, that should be right there. And now we've got a rectangle that sort of splits the balance, if you will, right? We got a little overestimate, but a little underestimate. Maybe those cancel each other out. Same thing for the second rectangle. I have a left and a right, but what happens if I choose it right in between? That midpoint, kind of same idea. I've got a little overestimate and a little underestimate. And last but not least, if I do the same thing over here, I've got a little overestimate and a little underestimate, okay? So in the big picture, someone was like, well, what if we can't get the exact value? Maybe we can approximate using the left, approximate using the right, or maybe this middle approximation is actually the best, okay? Well, it turns out we've actually got 2 other methods of approximating these integrals, okay? In particular, let's take a look at this one, okay? And so I'm going to go ahead and outline one of these shapes here, but I've got all these divisions, just like I did with the rectangles in the previous one, okay? But instead of going straight across at the top, like completely horizontal like this, we're now saying, let's connect the diagonal. Let's connect a diagonal. Let's connect a diagonal. Let's connect a diagonal. Okay. Now these shapes are called trapezoids. Okay. And so this leads us to our trapezoidal approximation. Oops. Okay. Pretty clever, right? We're like not fixed to the idea that it has to be completely horizontal across the top. And I think we can see that this is getting to be a lot closer to an actual value. Okay. Well, what's the other idea? The other idea was, and I'm not going to draw all of these, but if we take one of these divisions, okay, and instead of going from the left, or instead of coming from the right, or instead of going diagonal, what if we approximated it with a curve? Okay. And it turns out that this curve, right, is sort of a part of a parabola. Okay. So instead of using straight lines, now we're saying, well, what's the nicest curved shape we know? A parabola. And that is what we call Simpson's rule. Okay. So Simpson is the guy who's like, well, let's just use some curves and see if we can't get a better approximation. Everyone else was like, let's just use straight lines because those are maybe easier to work with. Okay. All right, so that's the main idea, but let's think about what the rules actually are, okay? So the trapezoidal rule, okay? Let f be a function defined from a to b. Then let's make a note here for ourselves that a and b, these are x values. So it's like where we start and where we stop, or like the bottom number on an integral and the top number on a definite integral, okay? Now we're going to cut this interval into n subintervals. So in other words, this is like how many vertical lines. Okay. So if I kind of go back to this one, I have like 1, 2, 3, 4 intervals. That would be n is 4. This one is 1, 2, 3, 4, 5, 6. So n equals 6. Okay. All right. Now, this trapezoidal formula, don't be scared, it looks a lot more complicated than it is. The trapezoidal approximation is we take the first y value plus 2 times the second y value plus 2 times the third y value plus we keep going and we double all of these y values in between, and the last y value is just going to happen one time. Okay? So this one happens once, and the last one happens once, and everything else we double everything in between. Okay? Then we're going to multiply that with this delta x, and then we're going to divide by 2. Okay? So let's go ahead and give this a go, see what we got. All right? So example 1 says, use the trapezoidal rule with n equals 4 to approximate the integral from 2 to 4 of the square root of 81 plus x to the 5th dx. Round function values to 4 decimal places and the final answer to 2 decimal places. Now, the reason that I'm being picky about our rounding here is because this is what it's like in your homework. So I want you to get used to like how the rounding goes. I don't want you to get a question wrong because you rounded wrong. That seems silly. Okay. All right. So I like to use a diagram to help me out. Okay. So I'm going to draw like from 2 to 4 because my A value is 2, my B value is 4. Okay. So I'm going from A to B. Now, I want to cut this space into 4 equal sections. Well, how wide is each section going to be? Well, if I cut it in half, that would be 2 sections, and each section would have a width of 1, but I want 4 sections. So 2.5 and 3.5, okay? And this means that each of these, this is what we call our delta x, is going to be 0.5, okay? Now, geometrically, if you're like a visual kind of person, this delta x is like the height of a trapezoid, okay? Now, most of the times in like elementary or middle school, you draw a trapezoid like this, right? And the height goes sort of like up and down. But in calculus, let me just go back up to this picture. We actually draw it kind of like sideways. So like it's standing up. So this is like the base 1, base 2. Here's my height of my trapezoid. Okay. All right. So we figured out our delta x. Now, let's go ahead and make a table. Okay, we're going to make a table of y values because if we go back to the formula, we see we're going to need once of the first y value, once of the last y value, and then we'll need to double everything in between. Okay. All right. Well, I didn't leave myself enough space vertically, so let me move this over here. Okay. So let's get a table going. Let's go maybe like this. All right, we've got our x and our f of x. And the x values are going to be the ones that we marked out along the line. 2, 2.5, 3, 3.5, and 4. Okay? Now, I'm going to take these numbers, 2, and I'm going to plug it into the function, square root of 81 plus x to the 5th. Okay, so let me just highlight that. That is the part that I plug in the function for. All right, now I've cheated a little bit. I've already calculated these all out, but this is a good time to just kind of pause and do your own calculations and see if your values match my values, okay? But when I plugged 2 into the function, I got 10.6301. Now remember, we're only going to 4 decimal places, so there's probably a lot more, but I rounded to 4 decimal places. All right, I plugged in 2.5, I got 13.3662. I plugged in 3 and I got 18. I plugged in 3.5 and I got 24.6215. And I plugged in 4 and I got 33.2415. Okay. All right. Now we plug everything into the function, into our formula. Okay, so sub into formula. All right. So my trapezoidal approximation, that's what the T stands for, with 4 subintervals. Okay, so n is 4. That's why I got to write that there. Equals. All right, we're going to have our first y value. All right, so f of 2. That only comes one time. Plus 2 times f of 2.5. Plus 2 times f of 3 plus 2 times f of 3.5 plus, let's double check our table because I think we're at the last one, right? Once, twice. So we're going to have f of 4 only happen one time. Okay. Now we need to do our times delta x, which is 0.5, and then I'm going to divide it by 2. Now, I won't show all the calculations here, but if I take all of these and add them together, I should get 155.847. And then 0.5 divided by 2 is 0.25. And when I multiply that out, I get 38.96175. But I need to round to 2 decimal places. So I'm going to cut this off and say 38.96. Okay. All right, so that's an example of how we use this trapezoidal rule, okay? So even if the formula felt super intimidating for you, all right, just like a lot of the other work we do, we're just breaking it down step by step, all right? So step 1, find your delta x. Right? That's what we did right here. Step 2, plug in all your y values. Step 3, plug it all into the formula. Okay? All right, let's take a look at Simpson's rule. So remember, Simpson's is the one that has not the straight line at the top, but kind of like a curvy, like a parabola, okay? And so same kind of idea here, all right? We are going to plug this into the formula. So we start with a y value once and a y value once, but then the ones in between, it's not too like trapezoidal. It's going to alternate. It's going to be 4, 2, 4, 2, 4, 2, 4, 2. You're going to keep going until you get to the last one. The last y value only happens one time. And then let me highlight something else that's different. Okay, so the 4 and the 2, the 4 and the 2, the 4, that's different. But also, instead of delta x divided by 2, I'm now going to divide by 3. And those are the qualities that make this rule have sort of the curvy bit on the top. Okay. All right, one last thing maybe that we should note though is that we have 2n here instead of n. All right, so s of 2n. But ultimately, we're going to follow pretty much the same steps. We'll just plug it into a different formula at the end. Okay? All right. So example two. Example two. Use Simpson's rule with n equals 2 to approximate the integral from 2 to 10 of x to the fourth over ln x dx. Same rounding, we're going to round function values to 4 decimal places and the final answer to 2 decimal places. All right, so let's find our delta x. Okay, now again, I like to draw a picture. So I'm just going to draw from 2 to 10. And I want to cut this into not 2 divisions, but I want to cut this into, all right, so 2n is 4. I want to cut this into 4 pieces. All right, well, from 2 to 6 to 10, that gives me 2 pieces, but I cut each one in half again. And now I've got 4 pieces, all right? So I've got like 1, 2, 3, 4. All right. What that means is that delta x equals 2, because I'm going from 2 to 4 is 2, from 4 to 6 is 2, from 6 to 8 is 2, and from 8 to 10 is 2, okay? But another way you could do this is you could take your b value, so 10, minus your a value, which is 2, and then divide it by your 2n. Okay, so let me write that in variables. B minus a over 2n will give you the same thing if you don't want to draw out a number line every time. Okay, so I think it's nice to know like what is it that we're finding, but also why that formula works. All right, now let's find our y values. Okay. All right, so I should have 5 y values this time. All right, f of x, and this time my f of x is this, x to the fourth over ln x. Okay, now kind of same as before, I cheated a little bit. I plugged in all my values before, so you can stop here and kind of do it on your own if you want. But for 2, I got 23.0831. For 4, I got 184.6650. For 6, I got 723.3114. For 8, I got 1969.7596. It's not going to fit. All right, for 10, we're going to make it fit. I got 4342.9448. Okay? All right. So double check my work, but I'm pretty sure those values are right. So we found our delta x, we found our y values. And then step 3, we're going to sub into the formula. Okay? All right. So I don't want to write t sub 4 because this time I'm using Simpson. So I want to write s sub 4 equals. All right. I'm going to plug in the first y value, f of 2, plus, then it's 4 times the second y value, plus 2 times the third y value, plus 4 times the next one, and then the last y value only happens one time, f of 10. Okay. Now, if I were doing trapezoidal, I would want 2, 2, 2 all the way across. Okay. All right, my delta x is 2, and I'm going to divide it by 3 this time because I'm using Simpson's, not trapezoidal. All right, like last time, I kind of cheated a little bit. I plugged it all into the calculator. For all the y values, I got 14430.3491, and I'm multiplying it by 2/3. Now, because 2/3 is like 0.666666666, like it kind of keeps going, I'm not going to write this as 0.6 because that would be rounding it, which is going to impact my final answer. And like I said before, I don't want to get a question wrong because I rounded wrong. That just seems silly. Okay. So I'm going to type this all into the calculator. I got 9620.232733, keeps going, but we're going to chop it off after 2 decimals. So we can type in a final answer of 9620.23. All right. So let's get this all on one page for you. But that's how we use Simpsons to approximate our area. Okay. So again, right here, this and this, like this is not an exact value. It's just an approximation. All right. Okay. So first half is all about approximating. The second half, I think we're really going to like because it's really all about using formulas that other people found to help us find an integral. Pretty cool. Okay. So integration using tables. It turns out that we have so many integrals out there that like, if you sat and did them out, you could do them, but sometimes they're so common in a lot of applications that someone actually took the time to just list out all the common integrals, okay? And so you can find these in your textbook. You're going to go to Table 1 of Appendix C, and I believe that corresponds to pages 709 to 711 in your textbook, okay? And so let's go ahead and highlight that. I recommend that maybe you pause the video right here, pull up your textbook online and just find those because that's what we're going to be referring to. I won't show you the actual pages just because I don't want to change screens too much, but I will write down the name or the number of the formula that it should correspond to. Okay. All right, so let's begin. Let's take a look at example 3. Whew. Now this one we could do, okay? We could do this using partial fractions, which is what we learned about last week. All right? But things of this form will always have the same answer. So let's use a shortcut here, okay? In fact, if you go to the end of your textbook, go to Appendix A or Appendix C and find your table, you'll see a formula that looks like this. U over A plus BU times C plus DU du. Okay, now I'm going to pause for a moment. This du and this du are not the same. Okay, so this u and this u are the same, but like we're literally just using the first 4 letters, A, B, C, D, okay? But this du is like our dx, like the d, whatever we have at the end of everything, okay? Now, this should correspond to formula 16, okay? And so let's identify our u, our A, our B, our C, our D, and our du, okay? So u, if I compare it over here, let's actually put this over here. U is going to be x, and du is dx, like the thing at the end, okay? A, B, C, D. All right, it looks like our A is 5, our B is 2, our C is 4, our D is, let's be careful here, it's actually going to be -3, Okay, so we got to grab the sign that goes with it because in the formula, everything is a plus. Okay, well, what does this formula say? This formula says that this integral is going to equal 1 over AD minus BC. So that's like A times D minus B times C times A over B, the natural log of A plus BU minus C over D times natural log of C plus DU. All of that, we have no bounds, so we got to have a plus C at the end. Okay? So if you get a question like this on a test and I'm like, use your table of integrals, I literally want you to find the one that matches, identify the important values, and then just plug them all in. Okay. Now, on an exam, I will be asking you to do also like partial fractions, like all the other techniques that we learned. But I do want to make sure if we have a question that says use your table of integrals, you literally just use your table of integrals. Okay. All right. Let's plug everything in. Let's see what we get. 1 over 5 times 2 minus 4 times negative 3 times 5 over 2 natural log of 5 plus 2x minus 4 over negative 3 natural log of 4 minus 3x plus c. All right. And that's literally all we do, but let's clean this up. Let's like turn this first thing into like a single fraction, and let's turn this negative and negative into a positive. I believe those will be the only things we clean up here, okay? So we should end up with, oh, and we're gonna distribute those out to those two terms too. So when you do all of that, you should get negative 5 over 46, natural log of 5 plus 2x minus 4 over 69, natural log of 4 minus 3x plus c. Okay. And again, that came from simplifying this and then distributing this to the first term and distributing it to the second term. Okay. My bet is if you distribute like this, so you get something like this, when you're typing it in on your online homework, it's just going to be easier to type in rather than like typing in so many different things. Okay, that's, I think, really the most important thing in terms of the simplifying as far as this kind of question is concerned. Okay. All right, let's take a look at example 4 and example 5. All right, so example 4. All right, we have the integral of 1 over x times the square root of 2x, or 25 minus x squared dx. Okay. Now, if we go to the back of our textbook, we'll find a formula that looks like this. 1 over u times the square root of a squared minus u squared and du, and I believe this corresponds with formula 29. Okay, so flip to the end, take a look at formula 29, should look like this. And what we really want to do is identify our u and our a and our dx, okay? So u, it looks like, is just x, which means du is dx. And my a is not 25. Okay, this is where we have to be really careful. This says a squared is 25. That means that a is just 5. All right, so I would say this is the only tricky thing about using the table is like finding the right formula and then making sure you match the parts correctly. All right, well, it turns out that this formula says we get negative 1 over a, the natural log of a plus the square root of a squared minus u squared all over u plus c. Okay. And now when we plug in the values we have, we're going to get negative 1 over 5, natural log of 5 plus 25 minus x squared all over x, close the absolute value, plus c. Okay? So even if this integral scared you a little bit at the beginning, once you found the formula, we just figure out all the pieces, plug it right in. Okay? All right, looks like we've got 2 more examples here. So let's take a look at example 5, all right? Integral of x squared over the square root of 16x squared minus 25 dx. Great. Now, if we look at the formula, okay, if we look at the formulas, we could look for a long time. We might not actually find one exactly like this. And so sometimes what we have to do is take a little bit of a u substitution before we get to a formula at the back of the book, okay? So here's what I mean by that. I'm going to let u squared equals 16x squared, okay? This means that u equals 4x and du equals 4dx. Or we can say 1/4 du equals dx, okay? Now, here's what we're going to do. We're going to rewrite this using this u sub. And so I'm going to bring this 1/4 out to the front. So I've got 1/4 the integral. Okay. Instead of x squared, I can divide that 16 over, and I'll have 1/16 u squared on the top. And on the bottom, I'll have the square root of u squared minus 25 du. Okay. Now, because I've got the 1/16 and the 1/4, I can bring that 1/16 out to the front. And I get 1 over 64, the integral of u squared over u squared minus 25 du. And now, when you go to the back of the book, we're going to find that this looks a lot like formula 44. Okay? So, formula 44 says, we're going to go from here. Okay? Formula 44 says, and let's not forget to keep that 1/64 out in the front. All right, it's going to be 1/2 times u, the square root of u squared minus a squared, plus a squared, natural log of u plus square root of u squared minus a squared, close it, close it. And yep. Why can't I keep track of all my parentheses? 1/2, close, close. There we go, bracket. Okay. So it's okay to get lost in the word, clearly. All right, happens to me all the time, but we're going to have 1 over 128. All right, our u was 4x, square root of 16x squared minus 25, plus a squared is 25, natural log of 4x, plus the square root of 16x squared minus 25. And we'll close that plus c. And this would be our integral of x squared over square root of 16x squared minus 25. Okay. Now, it might be hard to think about like what part goes where, but I think it's going to be strictly easier than figuring out how to integrate that. Okay. So it's almost like it's like the lesser of two evils. All right. Let's take a look at one last one over here. Example 6. All right. So I've got the integral of x over the square root of x to the 4th plus 1. Now, if we do a little u sub like we did for the last one, this time we're going to let u equal x squared. Okay. And if u equals x squared, that means that du is going to be 2x dx. And I'm just going to divide the 2 away because I see that I have an x dx here. So 1/2 du equals x dx. Okay, so let's sub all that in. I'm going to get 1/2 the integral of 1 over square root of u squared plus, now I know this is plus 1, but I'm actually just going to write it as 1 squared. Okay. Now the reason why I'm going to write it as 1 squared is because now if we go to the back of the textbook and we look up a formula, I bet we're going to find that formula 36 looks a lot like this one. Okay. So even though we know 1 is still just 1, by putting that squared on there, it helps us match the formula a little bit better. Okay. All right, well, what does this formula says? It says when we integrate this, that we get the natural log of u plus the square root of u squared plus a squared plus c. All right, well, let's plug in what we have. 1/2 natural log of x squared plus the square root of x to the 4th plus 1 plus c. Okay. So this second whole part, all right, so after we did the approximations, we spent a little bit of time looking at how we can just use the table in the back of the textbook to help us out. I do want to clarify one thing. So the first two, I hope you felt those were a little bit more straightforward, like we just matched the formula and then picked out the numbers. These are what the homework questions are going to be like on your online homework, okay? I wanted to show you 5 and 6 just to show you that U sub actually takes us a pretty long way. Turns out we don't even need, we can use the table and U sub to get to a formula in the back of the book. But I have not put any of these on your homework questions to save you a little bit of grief in terms of that part, okay? So most of your homework questions, all of them should look something like this, all right? So thank you so much for watching this video. Let me know if you have any questions, and I will be back on Thursday with a new lesson. All right, see you folks later.